Welcome to our lecture today. We are going to continue our topics on Laplace transform. Today we are going to see first we are going to look at initial and final value. This is one of the properties of Laplace transform that helps us to compute the initial value, which is mostly represented as f at 0 of the function, and the final, which is mostly represented as f at infinity value of the function. So by using Laplace transform, we can compute the initial value of any function by taking the limit of s times f of s as s approaches infinity, and when we try to compute the final value f infinity of the function, then we are going to take the limit of f of s as s approaches 0. So as you can see here, for an initial value of the function, which is the function at a t equal to 0 value, we take the approach where s is close to infinity, and to find the final value, which is f at time t equal to infinity, we are going to compute the value of f at s when s is approaching 0. This helps us to compute the final and initial values of a function. Let's see an example. For example, if we have a function f at t, which is equal to e raised to minus 2t cos 10t u at t. Mostly we know that this u at t is attached here so that would limit our function to anything greater than 0. So we can almost neglect or take that out with the understanding that t is always going to be greater than 0. So if we are asked to find the initial value of this function f at 0, then to compute f at 0 it is much easier to get first the f at s value of this. So we already know that the f at s value of this function, this e raised to minus 2t cos omega t, is always represented by s plus 2 because of here 2 over, and for the function we already know that cos 10t has an s over s squared plus omega squared. So when cos is 10, and with that time shift we have s plus 2 the whole squared plus 10 squared. That's s at f at s. So if we take s times f at s, then that value is going to be s squared plus 2s over s plus 2 the whole squared plus 10 squared. So by taking the limit of this, the limit of f at s as s approaches infinity would give us the limit of s squared plus 2s over s plus 2 the whole squared plus 10 squared. And in order to get this, the limit of this, I think I should write the limit probably here, limit as s approaches infinity. So in order to compute the infinity, the s approaching infinity thing here, then it's much easier to divide here by s squared. So we'll have what, s squared over s squared plus 2s over s squared. So if we divide the upper part, then we will also divide the lower part, which would give us s squared plus 4s. Here it would be plus 4 plus 100 plus 104. So we are going to divide this by s squared, and that would give us the limit of, this is s approaching infinity. So we have the limit of 1 plus 1 over s over 1 plus 4 over s plus 1 over s squared, which would be, all the s terms are going to be 0 because s is approaching to infinity, and that value is going to give us 1. So this tells us that the initial value of the function f of t, equal to e raised to minus 2t cos 10t is going to be 1. This is the initial value. By initial value we mean when t is approaching 0. So we got that by taking the s times f of s when s is approaching infinity. And this is handy for some functions where we cannot automatically compute the limit of that function with respect to taking t closer to 0. So if we take another example here for the final value, so we can compute, for example, let's take f of t to be e raised to minus 2t sine 5t u at t. So because of this sine function, we know that sine function has this value, so it's really hard to determine the value of t as t is approaching infinity. So in order to compute this, then we can use the final value theorem, which says that f at infinity can be computed by taking the limit of f at s as s is approaching 0. So our job is now to find what is s times f at s. So that would be s multiplied by the Laplace transform of f at s. So in this case, f at s is going to be, for sine 5t, e raised to minus 2t over sine 5t, we have 5 over s plus 2, the whole squared, plus 5 squared. Which means this is going to be 5s over s squared plus 4s plus 29. So if we take the limit of s times f of s as s is approaching 0, so that would be the limit of 5s over s squared plus 4s plus 29. So that would give us, as s is approaching 0, that value would be 0, because in this case we have s and s squared would be 0, so we have 0 over 29, which is 0. So that tells us that the value of f at infinity is 0, which is our final value. Mind you, we couldn't compute this as t is approaching 0 from the find function because of the presence of this sine t. We do not know at what value that sine function is going to be as it is approaching infinity. Alright, so that tells us final value and initial values. So just to review what we have just seen, the initial value and final value theorem tells us that initial value initial value theorem tells us that the f at 0 of any function can be computed by taking the limit of s times its Laplace transform as s is approaching infinity. And if we take the final value theorem, tells us that the f at infinity of any function can be computed by taking the limit of s times f at s as s is approaching 0. Do not forget these values. So for 0 we take the approach of s as it gets into infinity, and for infinity we take the approach of s to 0. Thank you very much. That will be all on this initial value and final value theorem.